In our last lecture, we have discussed that the brief introduction about structural analysis. So the structural analysis means determine the effect of loading, that is structural deformation, internal forces, stresses, support reactions, velocity, acceleration, and stability of the physical structure and their component. In today's lecture, I'm going to discuss about the what is static analysis and what is dynamic analysis. The structural analysis classified into two categories like static analysis and dynamic analysis based on the loading condition. The magnitude, direction, and the location of the loading varies slowly or constant with respect to time, then that is called static loading that we have seen in our last lecture. So the analysis of structure for that static loading is called static analysis. Suppose the magnitude, direction, and location of the loads varies very quickly, then that is called a dynamic analysis. The analysis or behavior of structure for that particular dynamic load is called a dynamic analysis. To understand the difference between the static analysis and dynamic analysis, I have considered here one simple example of a lift that we have seen in our daily basis life. So this the case scenario one is like it is a static case. This lift is static, it is not going to move any direction. And the second case is the dynamic analysis, which is going to move in upward direction or downward direction. Let's take the static conditions. In the static condition, if you see the free body diagram for this particular condition, so the force T in this rope going to be, let's call it as a T, the tension developed in the rope T, which is directly proportional to the weight of this object. So the mass is equal to 500 kg. So if we convert the mass into weight, so just 500 mass into acceleration due to gravity, which is equal to 5000 Newton. So the weight of this lift is 5000 Newton, which is going to act downward. So if we consider the equilibrium condition for this particular object, the tensile force developed in this rope T is equal to weight of this object. So the T developed in this rope is equal to 5000 Newton in a static condition. Let's consider another case in a dynamic case where this lift is going to move upward direction with some acceleration. So if you see the free body diagram for this dynamic case, the tension developed in this rope will be equal to the two component. One is the static weight of this lift, and the another component is the inertia force. According to Newton's second law of motion, if any object or any mass move one direction with some acceleration, so some inertia force will be generated in opposite direction to the movement. So in this case, the lift is moving in upward direction. The inertia component is developed in downward direction, which is equal to mass times the acceleration of the movement. So if you write a equilibrium equation for this dynamic case, the tension developed in the rope T is equal to the static weight of this lift plus the dynamic component developed because of this movement. So the total force equal to 5000 plus 500 into 0.5 times gravitational acceleration due to gravity. So the total force equal to 7500 Newton. If you see the importance of the dynamic analysis in this case, so if we consider the same lift, if we analyze it as a static analysis, so neglecting the inertia force, the tension developed is only 5000 Newton. Since the lift is moving with a considerable acceleration 0.5 times gravity, so the force developed is 7500 Newton. If you see the difference, it's almost 50% increased. So that is why the importance of dynamic analysis is when the object or mass is moving with some considerable acceleration or velocity, then definitely we should go for dynamic analysis. Otherwise, if we consider the static analysis, the differences are too much. So if we do static analysis for in this case by neglecting the inertia component, definitely this rope going to break at the service stage. So that is the important in civil engineering when we should consider the dynamic analysis, that we should understand this concept very clearly, so that we have to apply in our live projects. So static analysis means the static analysis use the mathematical modeling to analyze the behavior of structure under only static loading conditions. Let example, it can be a dead load, the weight of the structure itself, or it can be a live load, a people load, or some superimposed loads like a table, chair, all those things, and the environmental loads like such as wind, earthquake, and temperature changes. Even though although this environmental load is a dynamic load, it has been considered as a equivalent static load in the analysis. So that is why this is called as a static analysis. Here there is no inertia force component. So all in a static analysis, all the commercial software or even manual calculation, there is a method called stiffness matrix method. There will be these are those three matrices. One is force matrices, and this another one is the stiffness matrices, another one is the deformation matrices. In example, this is the plane frame analysis. Like this is a simple beam having 2 degrees of freedom on each end. So for this, the final matrix formation is the force matrix will be 4 by 1, and the stiffness matrix will be 4 by 4, and the deformation matrix will be again 4 by 1. So the first two component for this 2 degree of freedom, and the second two component for the another end, the 2 degree of freedom. In a dynamic analysis, it's more complex than the static analysis, as it's considering the effect of the inertial forces and the response of the structure to the time varying load. So let's consider a single degree of freedom system as shown here. This mass is attached to the spring of the stiffness K, and this is called dampness of this entire system, and this mass M is uh, moved a distance of u in this direction with the help of the force F, which is both applied at the time duration of t. So if we draw a free body diagram for this simple degree of freedom system, the force is F is applied in this direction, and the resistance and other force component developed in opposite direction. Basically these three components, the first component, this K into U, means the K is the stiffness of the spring, and the U is the displacement of this mass in this direction. So the force is directly the force due to this stiffness component, this called F stiffness, and the force will be directly proportional to the displacement of this object. And the second component is called C into U dash. U dash means, U means displacement, U dash is velocity, U double dash means acceleration. It's all are derivatives from this. The basic is the displacement. If the velocity is I in this direction, so the second force is called a damping force. The damping force will be directly proportional to the velocity component of the this object. And the third force is called the inertia component. This inertia force is directly proportional to the second derivative, which means the acceleration of this object moving in this direction. So if we write a equilibrium equation for this condition, the force F is equal to the static component, the K into the spring stiffness, and addition to the inertia component. The one is the damping matrix, another one is the mass matrix into acceleration. Damping matrix the velocity component, and the force matrix stiffness matrix into displacement component. So in a static analysis, we have seen that the force matrix, stiffness matrix, and the displacement matrix required to analyze the behavior of structure under only static load conditions. The dynamic analysis means addition to this force matrix, stiffness matrix, and the displacement matrix, we may record the additional mass matrix and damping matrix to consider the effect of the inertial forces and analyze the behavior of structure under the dynamic load conditions.